Hello everyone. I will talk about our paper called XAI4FL, Enhancing Spectrum-Based Fault Localization with Explainable Artificial Intelligence. As we all know, manually finding the program unit responsible for a fault is tedious and time-consuming. To mitigate this problem, many fault localization techniques have been proposed. One of the popular family techniques of fault localization is spectrum-based fault localization, or SBFL. SBFL is a process of deducing the exact source of a failure from a set of observed failure indications. Recently, XAI has been gaining popularity and has been used in many domains. However, the usage of XAI in fault localization is still limited. In this study, we propose XAI4FL, which utilizes XAI for SBFL. XAI refers to the method that we can gain insight into black box machine learning models and explain its output. In this study, we use a model-agnostic explanation technique that can interpret all machine learning models. To illustrate, we have data and a black box machine learning model. This ML model will predict the label of the data. By using XAI, we can get the explanation of why the model predicts the data to be such. SBFL techniques use statistical formulas to measure the suspiciousness of program units based on the execution traces. So here, we have a program and test cases. In every statement based on the results of the test, we have a red box that shows the statement covered by failing the test and a green box statement covered by passing the test. The more red box in the statement, the more suspicious the statement is. The XAI4FL takes an input of program spectra. It will build a machine learning model to approximate a function to measure the likelihood of whether the execution of a statement determines the outcome of the test case. We then apply the model-agnostic technique to get feature importance, which shows the statements that are likely to be responsible for the failing test case based on the model prediction. The intuition is that these statements are likely to be the locations where the faults reside. Let's discuss the XAI4FL architecture in detail. In the first part, we will obtain the program spectra from test cases. We use gzoltar to run the test cases and collect the execution traces. From the gzoltar output, we combine the results into program spectra. We can see here the example of it. 1 is show that statement executed and 0 is not executed. The label shows whether it is a fail or pass test case. Given a program spectra, we train a model to approximate a function to measure the likelihood of whether the execution of a statement determines the outcome of the test case. This function is then used to identify the important statements that are likely to be responsible for the failing test case. We use a random forest for the final classifier. We then apply the model-agnostic explanation technique, which is SHAP, to identify the statements that play an important role so the ML model predicts it to be the failed test case. We will apply XAI for every failed test case in the project, so for every test case we get the feature importance score. As we have discussed before, for every failed test case we will get the feature importance score. For example, here test cases 1, 2, and 3 have different feature importance scores. We combine these feature importance scores by considering 3 variants: mean variant, where we average the statement scores from different test cases. Then, max variant and min variant. We then rank the statement based on those combined scores. The dataset that we use for the evaluation is Defects4J, a popular dataset that has 395 real faults from 6 Java projects. In the RQ1, we want to check how effective these variants of XAI4FL are. For the metric, we use top K and exam scores. We use top 1 as the main metric, as many of the previous studies in automated program repair assume perfect fault localization. The results show that the max variant produces the best results. But the difference between these variants is not significant. For the next RQ, we will use the max variant for simplicity since it gives the best result. In RQ2, we compare XAI4FL with a simpler approach to get a feature importance score. Specifically, we use MDI, or mean decrease in impurity, to obtain a feature importance score from random forest model. To make it fair, we use the same model as that been used in XAI4FL. The result shows that from the 43 faults that are localized in top 1 by the MDI approach, 27 or 63% of them are already localized in top 1 by XAI4FL. The result shows that XAI4FL statistically significantly outperforms the MDI method. The lower results of the MDI method may be due to the feature importance scores that represent the whole model rather than only the failed instances. In our Q3 we compare XAI4FL with 5 well-known SBFL techniques based on the study by Pearson et al. Where they check the effectiveness of SBFL techniques. The techniques are D-star, Baronel, OCHI, Tarantula, and OP. The results show that the XAI4FL gives better results in both top 1 and exam scores compared to the traditional SBFL techniques. And the improvements for the top 1, which is our main metric, are statistically significant and substantial. We also found that the majority of faults that are localized in top 1 by D-star are also localized in top 1 by XAI4FL. The other 11 faults that are localized on top 1 only by D-star, 10 out of the 11 faults are localized within top 5 predictions by XAI4FL. The detailed results per project show that overall XAI4FL can localize 2 to 6 times the number of faults in top 1 compared to using traditional SBFL techniques. For the conclusion, we proposed XAI4FL, which is the first XAI-supported SBFL approach. We have built 3 variants of it, and the results show that the max variant gets the best performance. XAI4FL shows that it can statistically significantly outperform the MDI method, which is the simpler approach to getting feature importance. In this study, we show that XAI can be used to enhance performance through model interpretability, indicate by XAI4FL results that statistically significantly outperform the results from popular SBFL techniques in top 1. For the future work, we want to further improve the performance of XAI4FL by exploring other XAI techniques and designing a new XAI model for fault localization. Thank you.